Oh, hello, everyone. Thanks for coming to my talk. My talk will be about events in Fintech and a little bit about myself before that. My name is Lukáš Ševčík. I am a backend developer at kiwi.com. And today I would like to tell you a story. A story about how we transitioned and refactored from the state machines and how we changed our payment processing systems into event-driven systems and what we learned in the meantime. So let's start at the beginning with the state machines. Lots of applications start this way. So what is a state machine? Basically, state machine is a mode of computation or a system that has some defined states that the system can be in. You have game running, game over, game post. These are the states you have. These states have transitions that are defined that can switch between them. These transitions are triggered by events that happen in the system. For example, player dies, game switches from game running to game over. You need to restart and continue. You probably know that. Yeah. So if you think about it, by defining these states and all of the possible transitions and events, you can create a list of all of valid combinations or patterns that the system can be in. But looks simple, right? Question is, what can we build with such a simple system? Turns out a lot. Since we are in a Python conference, let's look at the Python lecture. When you write a simple statement, for example, x equals 42, and you want to run it through Python, the first thing that happens is Python lecture needs to process this statement and turns it into tokens. Python lecture is nothing more than a humble state machine. Basically, it goes through character by character, and each of the character serves as a trigger in the state machines. You first encounter character X, and the state machine switches to the name state. After you encounter space, you go back to the initial state, you encounter equal, and you go character by character like this, and you produce resulting tokens until you get to the end state. So this is the power of simplicity of state machines. You have this very simple concept, and you can build even more complex things like language lexers or even parsers with it. This is then processed by Python parser, which is also a state machine, but a little bit more complicated one. But still, you can see what can we achieve with a simple state machine. What are the benefits of these approaches? Well, it has some advantages. They are really simple. They are simple to define, simple to test, simple to reason about. They are also very efficient. When I showed you the lecture, you can basically take a simple chip that doesn't even have a RAM. It just needs simple registers. You need to define the states program the states, program the transitions, and you can have a state machine with a very simple chip computer. You don't need anything big. As I said, they are easy to test, but there are also disadvantages to this simplicity. What are those? The no memory of the fact that you don't need a memory with the state machine is also advantage and a disadvantage. It doesn't know how it got to the state that it's in. If you ask the state machine why are we in the game over state, it has absolutely no idea. Also, when your system grows and you need to define more and more states, things can get quite complex. You have your combinations basically explode of what can happen. And it has a lack of context. You don't know like where in the processing of the language are you. You don't know what should happen and stuff like that. They are kind of inflexible and harder to refactor. I will talk about it more. And let's also consider some other problems that we encountered when we with our state machines and that we used. Well, good old race conditions. Basically, you have two workers that work in parallel. Both of them read account state. First one reads account state 1000, second one reads account state 1000. And they say, okay, I will deposit 200. The second one will say, I will deposit 150. They write down the account state, and you will, in this case, you will end up with the account state 850, which is definitely what you didn't want to come to. And status refactoring. Your managers and your specialists, they love to come up with new things. Then you find out you need to refactor your states. You need to maybe add some more granular states. We didn't love that, and our services, when we refactored them, didn't love that. You need to go through every single usage of the state that you have, and you need to see if it affects you. You need to refactor it, and the refactors are pain in this case. So what will save us from these things? We introducing history to our system will save us. But before we go there, let's talk about events and events before we go to event sourcing. What are those? You may have saw different talks or read about it in different articles, and lots of things are called events there. But for the purposes of this talk, and so we can understand each other, let's define what are events and what events are not. So let's say you have a system that has a few endpoints, and it can, again, it can withdraw, or it can work with accounts, withdraw or deposit them. Now, on your API endpoint, you receive a request to withdraw money, and you store the request. You maybe put it into some queue, or you store it anywhere. In lots of places, you can see even this called an event. For these purposes, for our talk, let's talk it a command. Let's name it a command. Basically, some API is commanding you to withdraw money. As I said, you store it into the queue. Then you have, for example, some workers that process this queue, that consume this queue. And after the command is processed and executed, the worker emits what's called an event. And this is the event that I would mainly like to talk about today. The event is, in this case, money withdrawn. So it informs you that money was actually withdrawn and stores the fact, this history, into the database. Yeah, so as I said, the right part marked as event sourcing is what mainly I will be talking about today. So let's talk more about events. Events are immutable facts about things that have happened in the past. The immutable is the important part here. As they explain what happened in the past, you shouldn't change what happened in the past. It's a fact that happened, so it should stay as it is. They should be in past tense because, again, they are talking about what happened in the past, so name them accordingly, name them in past tense. They should contain all of the relevant data to you. So everything that you think you will need later when you will reconstruct the events, when you will look into the past, what happened, store it into the event. But I think they should contain mainly the domain data of yours. They shouldn't contain implementation details that can change. They are not that useful. And finally, we get to the event sourcing. Event sourcing is way about thinking in your system in terms of history, in terms of the events. You have a set of events, and instead of storing a current state, you store all of the history. Now, when you want to find out what your account is, what is the state of the account, you just go through your history, you sum up all of the events, and you get to the final state of the account. This gives you, as I said, complete history and complete audit trail. And you even get some kind of a time machine. You are able to go back and replay the system from the past and see exactly what happened, test what happens. You can refactor your application and try what would happen in this case. This gives you this ability. And audit trails, mainly for us in fintech operations, are very useful. Now, if my manager comes to me and asks what happened with this payment, now I can say, yeah, I know exactly what happened, instead of previously when I said I have no idea what happened, manager is not happy. I tried. Yeah. So what are the benefits of this approach? First of all, as I said, you have complete audit trail. You have absolute complete visibility into your system. You get the ability to reconstruct the past states. Thank you. You have ability to reconstruct the past states. As I said, you can go into the past and you can play with your application, try different versions, and see what happened. Now, it is much easier to solve race conditions this way because you are appending only. So each worker can append its events. Money was withdrawn, money was deposited, withdrawn, deposited. They just write it down, and eventually you read of all those events, and you got to the state of the account. And you shouldn't come to basically race conditions are impossible when using this. Yeah, and decoupling of the states. This was interesting for us. Mainly, maybe you have different clients that are interested in different states of your applications. Maybe you have some legacy applications that needs to support legacy states. So with this, you can have just simple logic in your handlers or wherever that can look at the states and compute, look at the history of your events and compute different sets of states from this and return different sets of states to your different clients. This is very easy to do when you have complete information and you are not losing anything in state machines. And eventually, when you get into the state where you need to process huge amounts of requests, you can go full CQRS or full. I will go back. Full CQRS, full event-driven architecture. That means you have already finished your right side of the diagram here. You can just create commands. You can create queues that will process them. And building this whole system, it's kind of, you are halfway there. So it is possible, it is doable. And then you can have those fancy architectures that you saw that can process millions and billions of requests. And it is possible to do that and fan out and have it parallel. Let's go back. And easy to adapt new business requirements. As I said, refactoring the state machines was not easy. You need to go through all of the states, see if it applies. Something happened. See if it applies to you. See if the refactoring is affecting this. But when you want to add new events, is not a problem, because right now in your application you are looking into history. So you are looking into, did this event happen? And if you add new events, new types of events, as long as you stick to the OCP, you are only adding new events. You are not updating or modifying the existing events. You can add as many events as you want. You can go more granular. You can add more events. It doesn't matter, since you are only looking into history. Did this event happen? Yes, basically what I said. You need to stick to OCP or open to addition, close to change. You need to just add new events, and you are good. You can add as much events as you want. Yes, this is what I will talk about. Yeah, is it all good? There are also challenges to these approaches. What's called eventual consistency. As I said, race conditions are not possible. You just add events, and you may add as much. You just add events, and then you look at the account state. What can happen is you look at the account state and you figure out that, oh yeah, we actually overdrafted the account. This is called eventual consistency. Eventually, you will figure out that you did something that was not wrong. But now you have complete history, so you know what happened, and you can work. You can compensate for that, basically, if it's possible for you. Potentially much higher storage requirements. Since you are not only storing current state of your system, you are storing all of the history. It makes sense. You need to store much more data. There is also higher complexity. Since you don't have a simple state machines, you don't just look at the state. You need to compute the state. You need to, there's added computation you need to do, basically. And you really should. In most cases, you cannot rely on event ordering. Most system can promise you at best at least one delivery. So you know you will have the event, but you are not sure what will be the order of the event. So you need to work around that, basically. So what solutions did we choose to solve this mostly? We use what's called saga pattern. So you write start and end events. Basically, start of the processing started, then you process your application, and processing ended. This allowed us to immediately see that something happened, and we can see when we try to do something else that this already happened and we shouldn't overdraft the account or something similar. This plays very nice with locking mechanisms. If you really need to have an order in your events, or if you need to make sure that account is not overdrafted, you cannot go back actually and compensate for that. Locking mechanisms are your go-to. Basically, you need to ensure that you have only one worker or one system that reads the events at one time. You can, when you have the database, you can go select for update or something similar. And the Saga patterns that I mentioned before allows you to have this window that the system is locked very, very small. You always only check if it's possible to start some process, and if it's possible, you start the process and you release the lock. You don't need to keep the lock locked during the whole processing when you use this. Then there is thing optimistic concurrency control. That basically means you are versioning the events. In this case, versioning means you have a version number that you are incremented by one. That means I am writing event 1. The next event with in the same stream or under the same aggregate should have number 2. If this should be checked when writing to your persistent storage. If you see that you skipped a version or something happened, it's not a simple incrementing. You basically reject the event and you say to your system, yeah, something bad happened, check what happened, this is a history, try again. If this is possible for you, if you can reject events, this is also very, very kind of simple solution that you can use and implement. Idempotent events. It is important. This is generally not only for event sourcing, for your handlers and for your events to be or your systems to be idempotent. Basically, when you call it multiple times with the same input parameters, it should produce the same result always. And caching a snapshot. This can happen with the complexity of your system. Basically, when you for example compute states from your history, you can cache these states. Then what you can write some what's called write through cache. That means every time we write a new event into the database, the cache is invalidated. So you need to compute the states again. But if you ask for a state much more often than how often you are writing events, this can be very beneficial for you. There is also what's called snapshots. Basically, you read through your history, and at a certain point in your history, you create a snapshot, which means you compute the state of your account, you store the state of the account, and next time you need to only look to your history only from this moment onwards. So we are creating snapshots in the history where you computed what happened. And that would be it. Thank you for your attention. Yeah, basically. Yeah, so maybe some closing thoughts. What I wanted to show you is there is no better or worse approach. Sorry, there is no better or worse approach. We saw this as a evolution, the event sourcing, we saw this as an evolution of the state machines. And hopefully you now see when the simplicity is good for you, when you can go for the state machines. You can see when the more complex approaches of event-driven systems are best for you, and you would go for it event-driven. So hopefully this is something that you can take from this talk. That's finally, thank you. Any questions? Yes, I think first. I'm not sure how.
Hi, so I have 2 questions. So typically people when they build accounts, they use like ledger pattern and double entry accounting. So how does it relate to your event sourcing solution? And then is there a specific framework you used for event sourcing, or did you build it from scratch?
Yeah, good question. Actually, when you think about ledger, it's basically event sourcing. You are stalling all of the history. So I would say this plays very nice with the event sourcing solution. You would have something that replicates the ledger very good, I would say. And for the second question, we build it from scratch. I didn't find anything that would satisfy everything that we need. It was not that hard, actually. I would say it was manageable. So I would say go for it. Try to build it from the scratch. Yeah.
So in event-driven architecture, usually there are people that follow standards for the events and people that have more free in the schema of the events. Like what did you follow in this case? Do you define a standard for the body of the events and metadata, or do you just keep it free and open?
Mostly free. We used what was important for us. We used all of the domain knowledge that we thought will be important to us. We stored them into the events. We didn't follow any schema. We very stick to the no mutating of the old events and append only into the events. But after that, just store everything you need. You think from your domain. I will reiterate, from your domain, and you know, it's your system. So you know, whatever you need, you can store it. You know. I think there was one. There's still. Yeah. Okay. Larry? Yeah.
Yeah, thank you for your talk. I have a question. How often do you store snapshots for your data in case of failure to recover steps, history?
Yes, basically you don't need snapshots really to recover. You just need them to ease the computation and you know, validating the state or getting to the state. With our use case, we didn't arrive at the state where we need snapshots, basically. We process payments, and at the, I am in the Fintech team that processes payments at kiwi.com, and we store events for each aggregate. For our use case, order or payment is the aggregate, and it doesn't have that much events. We just have a lot of aggregates, so we are solving these problems. And we stored that just basically a few years back. We don't need data, we delete them. Yeah, so this would be more interesting for, like, let's say a banking application. When you have a lot of movement on the account, you would probably need to store snapshots, but at that time, it depends a lot on how big your events are, what storage you use. Maybe if you know you have a lot of aggregation going on, you would use some columnar databases or something. And you see they are still very good at aggregation of the events. So basically, once you would arrive at problems, you would start snapshotting. But I wouldn't say you need to start from start. You see you have problems, so you think about it. You know, it depends on the system. You know.
Thank you.
Yeah. Still.
Normally, a financial transaction is connected to some other activities, and these other activities can fail. So would you start two events and then have some kind of rollback, or just not send an end marker? So how do you handle this if the two connected things, one of them fails?
Yes, so what we do, as I said, we use the Saga part, and we have the process started. And when we see that during the processing something failed, we just store event processing failed. And then we work from that. We see, okay, we need to somehow compensate. We need to refund this. We need to stop booking the tickets or something like that. So we then have observers based on these events that emit some commands or something that says we need to compensate for this failed event. But basically, to answer, you just store failed event, and then you emit some events based on that. Either you can have observers in domain. Some databases use the CDC, which basically they emit the events themselves. Depends what you need, but you can just store failed event. That is a thing. Yeah.
Thanks.
Yeah, finally.
Yeah, I have two questions maybe. So first one, maybe you could give some tips on keeping this OCP principle, open close principle for the events, because I understand if you define a schema for the event, and then let's say you change the field name, you cannot replay this event anymore, right? So you have to.
Yes, don't change field names. Yeah.
You have to. So maybe one is like you have to stick to the same field name forever. Like, do you have any other tips on how to like practically keep this principle?
Yes. I would say, give an event, like try to think beforehand what will you need. That will save you a lot of trouble. If you need to add to the specific event, only add new fields. And then when you try to replay, you need to think about that this additional field exists. But even if your application holds to the OCP, it only searches for the fields that it only needs and exist. If you have the older version of the application, or you have the application compatible with older version, then you can kind of get around that. but definitely don't rename fields. Just append new fields. Deprecate the field and add a new field if you need. I would very strictly not mutate anything there. So even with the fields inside the events and with the new events, I would just append.
Okay, thanks. And maybe another one is like, it's hard to understand for me. So you mentioned that you avoid race conditions when you use event sourcing because you just append events. But for me to understand, like if you have a sequence of events that needs to be processed in order, like, I don't know, you have some start event, like I imagine, just as an example, like you log into the session, you open the session, then you withdraw some money, and then you close the session. And you have to process them in this order because you cannot first close the session and open it. So if you have multiple workers processing those events, how can you make sure the order is preserved? Because it could be that event 1 starts processing, it didn't finish yet, and then the second event starts processing, it finished before the first one. You know what I mean? Like
yes. In this specific case, this is also what we do. We cannot start booking before it's paid. We use the locking, as I said. Only at what point only one worker can read the events, and then in that case, the worker 2 will need to wait for the first worker to stop processing or closing the session or anything, and then start writing. Because if you have this need that the events need to happen in some order and they need to be sequential, then you basically cannot get around locking that much. Otherwise, you would have the eventual consistency, and that can cause problems similar to the race conditions. I would say it's not exactly race. Well, depends what you call the race condition. In this case, the race condition is you end up in a state that is completely different than what it should be. You write two things into one field, basically. In the case that we talked about, it is more like eventual consistency and inconsistency. But yeah, if you need order, you need to make sure that you need to somehow make sure that the second worker doesn't start until the first ended. So either locking or something else, but locking is probably the easiest.
Okay, thank you.
Hi, thanks for the talk. My question related to the last question is about how to avoid the race condition, the race condition when you are assigning the ID of the event in order to know that there is a previous event when you are processing them. If you are assigning a sequential event, how do you avoid this order that it changed the expected order?
Yes, with the you are talking about the event versioning with the appending the one. Yes,
appending one, and you know that there is a previous one, but you are assigning IDs that I think I assume that you compare you check if there is a previous event that it has not been processed yet.
Yes. Basically, in this case, you need to do that as late as possible. Ideally, in your database should tell you do a composite primary key or something like that. And in this case, this doesn't help you avoid this. This helps you only figure out that this happened. And then you need to say, stop, we need to go back, something bad happened, compute it again. Go from start again. But this doesn't help you to prevent this. This only helps you to make sure, to know that it happened. So not sure if that answered your question, but yeah.
But I was asking about the race condition when assigning the ID. If there are two events that are being created at the same time and you expect it to be in order, or...
Yes, that can happen, and you will detect that it happened, and then you will reject both. So this is only the detection. It doesn't help you to prevent this. Okay. So this is helpful when you cannot afford loss and you want to write fast, and you are okay with this conflict, but it doesn't help you to prevent it.
Thanks.